Problem 8 gate AB shown in the figure is a quarter circle, 2.4 meters wide, hinged at B and resting against a smooth wall at A. Compute the reaction forces at A and B. So I'll present the solution using the principles of statics to simplify the solution so that we won't be worried about the line of action of FV, for example. So the technique is for the horizontal component of force, we locate the endpoints of the curve in contact with the liquid. So endpoints are A and B. Then we draw horizontal line. Then the distance between these horizontal lines to the endpoints would be the net height of the gate. So the net height of the gate is 1.5. Since the gate is 2.4 meters wide into the screen, so this is also 2.4. So the centroid, word FH is going to the right. It is below the centroid of the projected area. So supposedly this is at distance vis-a-vis from the centroid. But we will not solve for vis-a-vis this time because we're computing for the reaction components at A and B. At A, there's no vertical reaction because it is smooth, only horizontal reaction, we'll call that RA. Then for the vertical component of fluid pressure, total fluid pressure or pressure force, we draw vertical lines through the endpoints. So A, we draw vertical line up to the liquid surface, imaginary or real. At B also, then the volume or area bounded by those vertical lines, the liquid surface, seawater surface, and the curve will be the volume to be considered in computing the FV. So that is FV. And we know that the resultant force passes through the center of the circular curve. That's by principle. So supposedly that is XB, but there's a technique, as I said, wherein we will not compute for XB anymore. And we will not compute for ISA V anymore. So remember from by principle, because this is circular, the resultant force passes through the center. Then by principle of transmissibility of a force, we can move the components also at C. And that's why we will do that so that we will no longer solve for XB and this distance YB here. So these are the reaction components, vertical component at V at B and horizontal component at B. Only one reaction component at A. So for instance, if you want to solve for RA, then let's transfer first FH and FV at C. We can do that by principle of transmissibility. So forget about all this. Just concentrate on these blue reaction components and this yellow FH and FV transferred at C. So if we sum up moments about B, for example, summation moment about B equals 0, our equation is RA times 1.5, this is 1.5, then FH is passing through B, this is counterclockwise, then equals clockwise moment FV times 1.5. So cancel out 1.5, so that means RA equals F sub V. Then we establish a point B sub V times 1.5. We sum up moment about C this time. At C, considering these forces, 5 forces, B sub V times 1.5. So BH, FH, and FV are not involved. They act or pass through C. So B sub V times 1.5 radius, that's clockwise, equals counterclockwise moment RA times 1.5. So that means B sub V is equal to RA. And because RA is also FV, B sub V is equal to FV. So that's the idea. Then finally, we introduce this point here, call that D, so that RA passes through D, vis-a-vis passes through D, and only these three forces are involved, BH, FH, and FV. So clockwise moment positive, summation moment about D equals 0, BH times 1.5 plus FV times 1.5 then equals FH times 1.5. So cancelling out 1.5, BH plus FV equals FH. Take note that this equation is like summation forces X. You look at the equation. Oh no, because FV is RA. FV is RA. So it's like summation forces X. BH to the left plus FV, which is RA, plus RA to the left equals FH, which is to the right. So this equation is just like summation forces X after establishing that FV is RA. So we now compute FH. FH is specific weight of seawater. Bard H, which is 3.6 minus 1.5 over 2. So this is Bard H, that distance. That is 3.6 minus 1.5 over 2. So FH is 10.06, quantity Bard H 3.6 minus 1.5 over 2. The area is 2.4 times 1.5. So FH is equal to 103.2 kilonewtons. FV, on the other hand, is the better way is specific weight of seawater times volume. This volume here. And this volume is area of this figure times 2.4. Now, the area of this figure is easily computed by treating it as big rectangle minus quarter circle. So, FV is 10.06, quantity area of big rectangle 1.5 by 3.6 minus area of quarter circle pi over 4 or 0.25 by radius square 1.5 square. Then the width perpendicular to the board screen is 2.4. So FV is equal to 87.71 kilonewtons. Since RA equals FV, RA is 87.71 kilonewtons. Since vis-a-vis is also RA and RA is 87.71, so the vertical component of B at B is also 87.71 kilonewtons upward. Then finally, substitute in this equation to solve for BH. So BH plus FV 87.71 equals FH 103.2. So BH is equal to 15.49 kilonewtons leftward. So that's all for this problem.